Hello, hello. I just drank a lot of tea, and now I feel a rush of caffeine that's making me feel sick. Uh, I don't know, just Trader Joe's black English tea. What's my favorite kind of tea? I like my favorite type of tea is Indian milk tea. Extremely good. I like Indian tea because it's very um, has a lot of spices in it. It's very fragrant. And I like milk in tea for whatever reason. Some people think it's gross, but I like it when milk tea it gets like a film on top. I like the film on top of the milk tea. I don't know why I like it, but I do. Man, I wish people would get here on time. Okay, I'm just gonna start. You know what? It's been 3 minutes. Um, all right. Hello, class. Um, so for the last two lessons, we've been talking about torque. And today we're going to talk about another topic, and then after Thanksgiving vacation, we'll bring it all together. So today's topic is called rotational inertia, which is denoted by I. And rotational inertia measures how tough it is to start or stop rotating an object. And it's important to so an object that has a large rotational inertia will be very difficult to get it starting to spin. Okay. And if it's difficult to start it spinning, it's also difficult to stop it spinning. Okay. Important thing to note, though, is that rotational inertia is talking about how difficult it is to start or stop in the absence of friction. So it's a lot like mass, right? Mass is how difficult it is to start or stop translating an object in the absence of friction. You know, friction always makes it more difficult, but so mass is talking about how difficult it is to get something moving, even if you didn't have friction, if it was in outer space. Rotational inertia is the same way. It's how difficult is it to start something spinning, even if it were in outer space. Okay? So sometimes the rotational inertia is called moment of inertia. Just an FYI, you might hear it. Or sometimes it's just called inertia. Okay? One thing about the rotational inertia is that it depends on mass distribution. Okay, so where is the mass located? Okay, if I take this screwdriver, okay, most of the mass is located at one end, at this end. So that's going to affect the rotational inertia. Trying to see if I have other asymmetrical objects around me. That's it. It also depends on the axis of rotation. Okay, so, and when we talk about an axis of rotation, I can have an axis of rotation can be passing through a certain point. So I could have an axis of rotation that passes through this button, goes through that button. But then an axis of rotation also has an orientation. So if I have an axis sort of towards you guys through this button, that would be rotating it like this. Okay. If I have an axis of rotation through this button pointed this way, then that would be a rotation like this. Okay. So, and then I could also have an axis of rotation that's parallel to this, but about a different location. So maybe like this instead. So axes of rotation have both a location and a direction. So that the rotational inertia depends on both of those factors. Okay. So here's the picture I want you to have in your head. Suppose you have some axis of rotation. So if this is the axis of rotation, it means we're going to rotate it like this. So, if that was our axis of rotation and this were the calculator, it would be rotating the calculator like this. Okay. And then suppose we have a mass, which I will call M. I'm going to define R as the distance, the perpendicular distance from the mass to the axis of rotation. So you might have encountered this in your geometry class, where you have a line. So an axis of rotation is basically a line. And then you have a point. R is the perpendicular distance between the point and the line. Okay? So if you have a mass and you have calculated R, the rotational inertia is the size of that mass times R squared. So why this is, and this is just a definition, so why does this end up being a useful definition we'll understand in the next lesson. But yeah, it turns out that this measures, this combination of variables quantifies how difficult it is to start and stop rotating an object. Okay. What if you have multiple objects that are rotating about the axis and you're going to rotate all of them together? Okay. Then maybe this is M1 and that's R1. Okay, so there's a good question in the chat. So, so yeah, I guess if something is not spinning, if you're trying to stop an object from spinning, yeah, you would use friction like brake pads. But it's a matter of how much friction would you need to use to stop the object. So maybe we should put it that way. It's how much friction would you need to use to stop something from spinning is related to the rotational inertia. Okay. So in general, oh Oh, you know what? I think I have a baseball bat. Let me grab a baseball bat. Okay, so I have a baseball bat under my bed. I have a baseball bat under my bed. Don't invade my home. Um, so if you're holding the baseball bat, let's say I'm playing baseball, and I swing it, okay, the inertia is measuring essentially how much torque do I need to get the baseball bat swinging. Okay, so something that has a more rotational inertia will be more difficult to get the bat started. Okay, so it actually depends on both the weight distribution of the bat. So the bat has more weight towards the end, right? And it also has to do with how far away that mass is from the axis of rotation. So if I'm swinging a bat like this, then the axis of rotation is essentially right here, okay? If I'm holding the bat differently, if I'm swinging it like this, I don't know why I would swing it like that, but that's a different axis of rotation, okay? So that it's actually a lot easier to twist the bat when I'm holding it like this. It's a lot easier. So that has less rotational inertia. This has more rotational inertia. Okay? I should go to a batting cage. I haven't done that in a long time. All right. So if you had multiple masses, and a baseball bat is multiple masses because it's made out of atoms, okay? All of those masses are going to be, in general, different. All of those masses are going to be different distances from the axis. So maybe M2 is right here, and it's a distance R2 away. Maybe M3 is right here. It's a distance R3 away. Maybe M4 is right here, and so on. Okay? In the case where you have multiple masses, all right, the rotational inertia is the sum of over mr squared. So you just sum over them. The units of rotational inertia are easy to determine because it's a mass times a distance squared. So it's kilogram meters squared are the units of rotational inertia. All right, so let's do an example. Suppose we have a square of 1 kilogram masses. So these are all 1 kilogram. All right. All right, and the side length of the square you know, I keep thinking about your comment, and when I say in the absence of friction, I mean in the absence of friction from the axle of rotation, okay? Because a lot of times the axis of rotation has a little bit of friction, so even if you rotate something, it has a little bit of resistance from that, so in the absence of that. So this is a 3 meter on a side square. okay? And I would like to calculate the rotational inertia about the center of the square, about an axis that comes out of the page through the center of the square, all right? So we're rotating it like this. So and I'm going to call that axis A. So I want to get the rotational inertia about axis A. So if we do that, I notice that I'm going to have 4 identical terms. There's going to be a term for each of the masses, okay? And each of these masses is a certain distance away from that axis of rotation. So it would be this distance right here, okay? Now what is that distance? Well, the diagonal of a square is 3 times root 2, okay? And this is half the diagonal of a square, so 3 times root 2 over 2. So that's 3 over root 2 is the R value for this mass, okay? So if I calculate the rotational inertia due to that single mass, it's going to be 1 times 3 over root 2 quantity squared. But each of these 4 masses is the same distance away from the axis of rotation. So they're all the same mass. So all 4 of these terms are going to be the same. So I'm adding up 4 identical terms, so I can just multiply my answer by 4. Okay? So this gives 4 times 9 is 36 over 2, 18 kilogram meters squared is the rotational inertia about that axis. Now, what if I chose a different axis? So this is axis B. So notice how axis A is out of the plane of the page, and axis B is in the plane of the page. So axis A is spinning it like this, okay? Axis B is spinning it like this, okay? So what if we wanted to calculate it about axis B? Well, here's the thing. If you have a mass that is on the axis of rotation, it has an R value of 0. Okay? Like if I put a mass right here, it's on the line, so its distance from the line is 0. Okay? So and if its R value is 0, then its inertia is 0. So any mass that is on the axis of rotation does not count towards your rotational inertia. So these 2 masses do not contribute because they are on the axis of rotation. These 2 masses do contribute, and both of them are 3 meters away from the axis of rotation. So I have 1 times 3 squared, and there's 2 masses making identical contributions. Okay? So this gives 18 kilogram meters squared. So that was completely by accident. All right? So what that means is for this square, it is the same level of difficulty to rotate it this way as it is to rotate it this way. Okay? That was purely by accident. If I had chose a different axis, they would be different in general. And the one with the larger rotational inertia would be more difficult to rotate. It would be more difficult to rotate it that way than in another way. Okay. So this is pretty much what I taught last year in terms of rotational inertia, all this stuff. So now we're going to get to the new stuff. The first thing I want to talk about is the rotational inertia of a non-uniform rod. Okay? So if you have a non-uniform rod, let's say I So I equals sum over mr squared. And so when we have a non-uniform rod, what we're going to do is we're going to take the limit as the size of the masses goes to 0. And then just like in the last lesson where we had the limit of a sum becomes an integral. Okay, so this becomes the integral of dm times r squared. Okay, now because it is a rod is a linear thing, we can use the linear mass density. So dm dx is lambda, which means that dm equals lambda times dx. Okay, so and furthermore, r, if you have a rod that you are rotating about some axis, the distance from the axis, I should say the inertia of a non-uniform rod about a perpendicular axis. So this axis is perpendicular to the rod. Okay. In this case, if we look at this point, say at x, it's a distance r away from the axis of rotation. So we also have r equals x in this case. So putting all that together, we get that it's the integral of x squared times lambda dx. So this is the rotational inertia of a one-dimensional rod. Okay. So let's do an example, which is what if we have a rod has lambda of x equals 5 minus 5/4 x squared. And we want to, it extends from x equals minus 2 meters to x equals plus 2 meters. Okay. Calculate I about an axis through x equals 0 and perpendicular to the rod. Okay, so so here's the rod. Okay, here's x equals 2. Here's x equals minus 2. Here's x equals 0, and there's our axis of rotation. So we're spinning it this way. Now, what does this linear mass density look like? Well, this looks like a concave down parabola. Okay, so something like this. So what that means is we have the most mass in the center, and then less and less mass as we go to the outside edge of the rod. So if you were to graph it, the linear mass density would look like this, actually. So concave down parabola, most of the mass is in the center. So really what this boils down to is just doing the integral. So we have the integral of x squared times lambda dx. Okay. And the limits of integration are going to be the limits of the rod, okay, which is from minus 2 to 2. So we have to do this integral. I'm going to plug it into Wolfram alpha. I'm waiting for my computer goes super slow on streaming, so takes me a second. Integrate x squared times 5 minus 5/4 times x squared from -2 to 2. My computer is going so slow, it would probably be less time to do this by hand. But the final answer is 10.7 kilogram meters squared. Okay? So that would be our answer. All right. So the second new topic is how do we calculate the inertia of a non-uniform disk? Okay, so we're going to calculate the inertia of a non-uniform disk. So a disk is different from a rod. A disk is like a plate that's spinning. A rod is like a baseball bat. So how do we do that? We're going to do this about an axis. Through the center, through and perpendicular to the center of the disk. Okay, so let's draw this. Okay, so if we were to look at this from the top, we have here's our disk, and there's the axis of rotation coming out of the page. Okay, so rotating it like this. If we were to look at it for a side view, if you look at a disk like a spinning pizza, yeah, except it's a spinning pizza, and where the pepperonis are, if you think of the pepperoni as the mass, you're putting the pepperonis, you're concentrating the pepperonis at different locations. Okay. Side view. Here's the edge of the pizza. Here's the axis of rotation. Maybe we can draw a 3D view as well. So 3D view, here's the spinning pizza. Here's the center. Here's the axis of rotation. Okay? So when we have a... so we're actually going to use the same exact formula. So the inertia is the integral of dm times r squared. Okay, that's the formula. But here's the thing. All right, here's the thing. Because this is a disk is a planar two-dimensional object. Okay, so we don't have mass per length. What we have is mass per area. So kilograms per square meter. All right. And whereas mass per length is called lambda, the linear mass density, mass per area is called sigma, which is the I don't even know what you call it. I just call it mass per area. It's typically denoted by sigma. Similarly, the mass per volume is denoted by rho. So these are all versions of density. They're just density expressed in a different number of dimensions, okay? If we lived in a one-dimensional world, then density wouldn't be mass per volume. It would be mass per length, okay? If we lived in a two-dimensional world, density wouldn't be mass per volume, it would be mass per area. If we lived in a four-dimensional world, density would be mass per hypervolume. Okay? So if we multiply both sides by dA, we get dm equals sigma times dA. All right? So we can plug that in. We get the integral of sigma times r squared dA. But now that leads to the question, well, gee, what the heck does dA even mean? Okay, we know the integrals always have a d something, and that something has always been a length. Okay, but now we have a d area. That's a two-dimensional thing. So what does that mean? Well, let me tell you. This is a circle. The area of a circle, the area of a circle is pi r squared. So what if I take the derivative of that formula and I do dA dr? All right, that's going to give me 2 pi r. And then I multiply both sides by r, and I get that dA is 2 pi r times dr. Okay, so this little derivation relied on the fact that this is a circular disk. Okay, so its area is pi r squared. If you had something that was not a disk, you would need to use a different formula. But we're not going to worry about that. Sort of the subject of multivariable calculus is figuring out what do things like this mean. Okay, so if you took a class in multivariable calculus, that's what you would learn about. But we only need sort of in this class, we only need sort of a simplified understanding of multivariable calculus. So that for you, all you need to worry about is dA is 2 pi r dr. So plugging that in, we get sigma times 2 pi, and then we have the r squared multiplying this r, so we have r cubed dr. All right, so this is the rotational inertia of a non-uniform disk. So sigma is the density, and it depends on r. Okay. The other thing I wanted to talk about that that we'll review later, or that we'll use later, is the total amount of mass is going to be the integral of dm, which is going to be sigma, the integral of sigma dA, which is going to be the integral of sigma times 2 pi r dr. So we're going to use that later, that the mass is the integral without the extra factor of r squared. Okay? So let's do an example. A disk has sigma of r equal to 5 over r kilograms per square meter. Those are the units, right? It's mass per area, so kilograms per square meter. And radius, 3 meters. So we want to calculate the inertia. So first of all, let's just interpret this mass per area. If you've ever seen a graph of 1 over x, it comes down from infinity. So this has a linear mass density that kind of looks like this. So it has actually infinite density in the center. And then that density gets smaller and smaller. So it has more mass concentrated at the center than it has at the edges. So it's kind of like a top almost. You know, the top at the end of inception, the top at the end of inception. You know how it has more mass in the center than it has at the edges. So it's sort of like that. So we're calculating the inertia. We're doing the integral of sigma times 2 pi r cubed dr. So plugging in for sigma, we get 5 over r. Okay, and then we get times 2 pi r cubed dr. Now, what are our limits of integration? Well, we have to look at all the different radii of the disk. So so what we can see is that we think about the disk as a bunch of concentric rings, and we can see that the innermost ring has radius 0, and the outermost ring has radius 3 meters. So this integral goes from 0 to 3, all right? Because r is representing a radius. So the smallest radius we have is 0, the biggest radius is 3. So this is 10 pi times the integral from 0 to 3 of r squared, which is going to be 10 pi over 3 times 3 cubed, which is going to be 90 pi. 90 pi kilogram meters squared is... My bat dropped. Okay. You okay, Bugs? All right. So one more item for today, which is, what if we want to know the inertia about a different axis? Okay, so there's a thing, it is called the parallel axis theorem. Okay, and so what we want to consider is, suppose we have a blob, okay, and maybe this is where the blob's center of mass is, okay, and here's an axis that passes through the center of mass, okay. So suppose we've calculated the rotational inertia about an axis going through the center of mass. Now, what if we have another axis that is parallel to the axis through the center of mass? So that's why it's called the parallel axis theorem. So what the parallel axis theorem says nothing about how is a rotational inertia about this axis related to a rotational inertia about this axis. But what it would say, it would relate the rotational inertia this way compared to the rotational inertia rotated about another axis that is parallel to it but passes through the object at a different location, okay? So what we want to know is, what is the rotational inertia about this other axis that is shifted but parallel? And it turns out that it depends on how far you shift it. We'll call that distance d. So the parallel axis theorem says that the rotational inertia about this other axis is equal to the rotational inertia you calculated about the center of mass plus the total mass times of the object times the distance that the axis is shifted squared. So the proof of this, if you want to see the proof, you can ask me during office hours. But in the interest of time, I'm not going to prove it. Okay? So that's called the parallel axis theorem, and it's really handy. There's a question, why is it 2 pi r cubed? The reason it's 2 pi r cubed is because we have the d area is 2 pi r, and then the definition of rotational inertia has r squared. So that r squared here multiplies the factor of r in dA to get r cubed. Okay. Okay. So one of the interesting facts about the parallel axis theorem is that d squared is a non-negative number. Okay. So this is a non-negative number. So what that means is that the smallest rotational inertia you can get is about an axis through the center of mass. So the center of mass, if you have an axis of rotation that passes through the center of mass, that's always going to be the easiest way to rotate something. If you rotate something about an axis that is not through the center of mass, that is more difficult. So if I have a baseball bat and I find its center of mass, if I just move try to balance it. So the center of mass is about right here. So if I hold the baseball bat and I rotate it about its center of mass, that's the easiest that it gets. Okay? If I rotate it about a parallel axis that is away from the center of mass, like right here, oh my gosh, that's difficult. Way more difficult to rotate it that way than it is to rotate it this way. Okay? So it's easiest to rotate something through the center of mass, about an axis through the center of mass. So let's do an example. What is the rotational inertia about an axis through the edge of the previous disk? Okay, so what if we weren't rotating this disk about this axis, but what if we rotated it about its edge? So instead of rotating it like this, we're rotating it like this. Okay, so the axis of rotation is now here. Okay, the axis of rotation is now here, so we're rotating it that way. So basically, we already calculated we already calculated the rotational inertia about the center of mass, because when we did the last example, our axis of rotation was through the very middle. Okay, and this is a symmetrical object, so the disk center of mass is in the middle. So I know that the rotational inertia about the center of mass is 90 pi. Okay, and the mass we're going to calculate in just a moment. How much is this axis shifted? Well, the radius of this disk was 3 meters, so that means that these axes are 3 meters apart. Okay, so my d squared is going to be 3 squared, and so now I just need to do the mass. And so that's why I also derived this integral right here for the total mass, was purely so that we could do the parallel axis theorem. So let me just work that out really quickly. So it's going to be the integral of sigma, which is 5 over r, times 2 pi r dr from 0 to 3. So that's the integral of dr from 0 to 3. So that ends up being 30 pi. All right. So this is 30 pi. 9 times 30 pi is going to be 270 pi. And so this is going to be 360 pi is the rotational inertia So it increased by quite a lot. All right. So that's my lesson for today. And I will see you in the Zoom room for an important discussion regarding if you're an IB student, I have an important discussion for you guys. Okay, so I'll see you.